The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, on the take-home exam, you did very well. I think the average was 88. It's very comfortable. Means everybody has learned something. So I think you'll say that I took a quick look at Jonathan, read very carefully, and overall I'm very pleased. I was impressed. There are a lot of math. Everybody reading down a lot of formulas. Okay, so the last is the best. And after today, you can go out, celebrate, hopefully. And we have a new president. You hear it? Okay. So what I was planning to talk about is on the molecular dynamics simulation. And really how they emphasize in the analysis of molecular dynamics simulation. So molecular dynamics simulation, conceptually, is very easy, right? What we want is actually most of the molecular dynamics simulation nowadays is based on classical molecular dynamics. And in fact, people think it's done, so the chalk, I like this thick chalk. No more. We'll have to use a different one. Okay, so the classical molecular dynamics is F equals ma, right? And so force equals ma. So if I have, for example, a simulation box, I have a crystal. I want to simulate its properties. And what I have, Newton's second law will tell me the mass of the ith atom, ma. So the acceleration of the ith atom, right, equals the force acting on the atom. So we have the force of all the other atoms, J equals 1 to n. That's the n is the number of atoms I'm simulating in the domain. And Fij, so that's the force acting on the specific atom. And of course, J doesn't equal to I. So that's the concept, right? It's very easy. And in fact, you have a anytime you give you say when a new student come in, you say, okay, this is the easiest. You start from here. Of course, you can think about your task then is doing integration of F equals ma, and you make sure that you have the proper potential, the force, right? Remember, the force equals the gradient of the potential. Right, so we need a proper potential, and at least conceptually, we had discussed in this course different potentials: Wonders potential, ionic potentials, covalent potential, so all those potential interactions. And the reality is, for each different material, when you do classical molecular dynamics simulation, the different material, people have spent a lot of time to put the proper potential so that they can reproduce some of the material's basic properties, like a melting point. When you heat it up, it melts, and or the mechanical properties. And because those are not potential from first principle, when I say first principle is quantum mechanics, right? Those are the classical potential, and typically you start with some concept and you put in the feeding parameters adjustable parameter to say these are the best set of parameters for those materials. But we're not going into discussion how to construct this potential. People typically, if you are able to construct the potential that's more general, many people use, you have already achieved a good success in this field. It's not easy to construct those potentials. And once you have the potential, this is second order derivative. You have the potential, you do your integration, right? And you want to find the position of the atoms, molecules, as a function of time in your simulation domain. So we can do the integration. So for example, the second order derivative, we know, let's drop the vector notation. So the second order derivative, drop the vector, I and dt squared equals Ri and t plus delta t. I use a central difference method, for example, and plus R t I t minus delta t minus 2 R I t. This is a time integration over and 2 delta t squared, right? So if you go to check the accuracy of this, this is actually of the order of delta t. This is the fourth order, so fourth power. So that's you actually have a relatively high accuracy when you use the central difference method. And then I can, if I write this, I can do you choose a time step. So this is a explicit method. You choose a time step, you advancing in time to find the position of the atoms at the next time. So you use the, say the next time is t plus delta t. You use the information, previous time step, the current time step, and previous time step. So I can integrate, I can march in time t plus delta t. And what I have here is then this one is, if you look at the Newton's second law, is really just the F divided by m. So what I have here is 2 Ri t minus Ri t minus delta t, right? And then I have the derivative of the acceleration, which is 2 delta t squared times the force acting on this atom in that specific direction divided by mass. That's my acceleration. And I know if I do this, what I'm accurate is 2 delta t fourth power. That's the terms that I dropped. Right. So this is to the fourth power is quite high numerical accuracy. And what's important is your time step, right? You say, okay, I'm going to accelerate my integration. I choose a very large time step. But remember, your time step has to be smaller than the physical process that goes on. Right? If I have atoms oscillate 10 to the 14th hertz, that means 10 to the minus 14th second or period. Then my delta t has to be, if I want to capture 1 period of the atom oscillation, you say that the sine function, I have to at least how accurate I say, okay, maybe I'll take 1/10. That's not very fine points for a sine function, you know. Right? So you can say then easily you get to femtosecond and very small time steps. And because of that, your integration time, you want to simulate the event that lasts a nanosecond, right? And nanosecond 10 to minus 9, if you start from 10 to minus 15 time step, you can imagine that's a lot of marching and a lot of computation. And each time step, you have to recalculate the force because of the atomic position change, and that will change the force interactions. So this is time. And with this, you can also calculate the velocity, right? Velocity of the at time t is just the gradient derivative, right? So we have the derivative of di dt, then I have ri t plus delta t, which I calculate in this time step, and I have rit and divided by delta t. And the disadvantage of this compared to central difference, this accuracy is lower. It's only t squared. And but it's lucky that this doesn't quite affect. This does not, in fact, does not affect my calculation of Ri, because my Ri calculation is independent of the velocity. So my velocity is not that accurate. My position is much more accurate. Depends on the time step you take. So that's easy, right? So in principle, you can write a code and do this calculation quickly. And the key question is how do you do your analysis? How you understand your analysis? Doing a numerical simulation, many times people like to say I'm doing a numerical experiment. Right? I don't like that terminology. But if you are doing computation, you like to say you're doing numerical experiment. The question is how you analyze your experiment, right? So what we're going to discuss, focus, is really the statistical foundation of numerical analysis. One more comment is, before we go there, is that when you do molecular dynamics simulation, I already said your time step has to be very short. Let's say if you do solid, you have to go to femtosecond or even sub-femtosecond. Depends on the oscillation frequency of the atoms. And the other is the number of atoms you can simulate. Right? And if I think about I want to simulate 1 micron cube, right? And if you see the typical, let's say silicon crystal, right? A silicon crystal lattice constant is about 5 angstrom. So in a 5 angstrom cube, there are 8 atoms. And a 1 nanometer cube, that's say 8 times 8, 64. And the 1 micron is 10 to the 9th power, right? Because there's 3 order magnitude higher in each direction. And that's a 10 to the 9th times 64. That's the number of atoms you got in 1 micron cube. And with that many time steps, and that needs very high powerful computer to even simulate 1 micron. So that's very hard. And typically people do periodic boundary condition. So they try to simulate, use a much smaller simulation box, right? And you have molecules or atoms in the box. And the next moment, this atom can move out of the simulation box. And the way that cleverly taken into this moving out is in the opposite direction, opposite boundary. So here it goes out of boundary, and it comes in, this atom comes in at the position, at the velocity, the corresponding position on the opposite boundary and the velocity that they exit. So this is a trick that people use, periodic boundary condition. And with that, you hope to recapture the effects of infinite simulation, right? Anytime you use a periodic boundary condition, you actually say in the specific direction where it's periodic, it's infinite. And there are also artifacts that's caused by this periodic boundary condition, as you will see, much easier once we get into the statistical aspects. And let's look into the statistical foundation. And first, in chapter 4, when we do the statistics, we introduce the concept of ensemble average. Right? In the old days, you do not actually trace the trajectory, the time trajectory of atoms. Remember, molecular dynamics is looking, the way we describe it is looking into the time trajectory of the atoms. And when we discussed the statistics, we said that's too complicated. We're actually going to do ensemble average rather than time average, right? And then we introduced the concept of ergodicity, our system for ergodic system, the ensemble average equals the time average, right? So the of course, the time average, if I have a quantity, this quantity is a quantity in phase space, for example, is a position and momentum of many particles. Right? I'm just using R represent maybe millions or billions of atoms, position and corresponding momentum. And when I do the time average of this quantity, I say this is, I observe this quantity over a certain period of time, starting anytime t plus delta t. So this origin, if I do my average correctly, and this origin doesn't matter. So here I have, this is RA, that phase space variable. For example, I can write the potential energy or kinetic energy or total energy in terms of the energy of every particles. And this is the total energy. I average it over a certain amount of time, right? So here, this R, remember, is a function of time. Momentum is a function of time. And I integrate, and that's the definition. If I look long enough, I get my average quantity, energy or momentum or pressure, right? The shear stress, all those quantities of the system. So this is the time averaging. And then when I do the ensemble average, right? Ensemble average of this quantity, I use a bracket. And remember, ensemble average is, I look at the probability function, right? We say microcanonical ensemble, each of the system in the ensemble is equal probability. Canonical ensemble is Boltzmann distribution, or we also introduced where the Gibbs ensemble there, where there is not only constant temperature, but also mass flow flux within ambient, right? So at the end, when I do the ensemble average, I average it over the probability, right? So the ensemble average is, I will have this phase space variable, R and P, and then I integrate over the phase space variables. And then I have my probability distribution, right, for n particle in the system, and R and P, and this is my integration. When I do double, I really mean many, because R and P is all the particles, momentum, and position. So ergodic system means my time average equals ensemble average, right? And in the past, we had really follow this trajectory. When I saw Boltzmann equation, I simplify this n particle distribution function into one particle distribution function. And I do the average velocity or heat flux as we have been doing. And when you do molecular dynamics, you're simulating time trajectory. So you're really interested in how I'm going to do the time average to get the quantities that I'm interested in. For example, if I want to compute the thermal conductivity, viscosity of the system, right? I will look at the atomic positions as a function of time and how I can extract this information that I'm interested in. So those are the questions. And let's look at, I'm interested in the property, right? Thermal conductivity, electric conductivity. And so in general, those are the response. If I, so let's discuss the response function. And let me look into a system that is initially at equilibrium. So system, equilibrium system. And the system Hamiltonian, right? The Hamiltonian, typically you can understand the Hamiltonian as the kinetic energy plus the potential energy. So the system Hamiltonian is H0, equilibrium. Let's say the volume is V. And then I'm going to give a disturbance to the system, right? I push the system, I push every atom, or I somehow inject some heat. So right now my disturbance, I'm going to say I'm going to give a small disturbance and uniform through this space. And this doesn't really matter. You can extend to long uniform. But because I have a perturbation, due to a force, so I use a force to perturb it, and because I'm applying force, the system Hamiltonian, the energy of the system will change, and that change is h prime, right? Small change. So I will say this is the perturbation to the Hamiltonian of the system, and I can write this perturbation because this is the force applied. So this will be related to the position and kinetic energy or of the each atom in the system, right? So this relation, Hamiltonian, is expressed in this perturbation, and this is the force applied, and I do a normalization to the volume, so I have my volume there. And I put a negative sign, that doesn't matter, because that could be absorbed into it, right? So this is my perturbed Hamiltonian. And now, so this is really the what is perturbing due to this force to individual atoms or molecules, right? And sometime later, I want to look at the response. I want to look at how the heat flux change, how the shear stress change, right? And the shear stress, again, is reflected by another quantity. Let's say this is a B. Again, is the individual phase space variable, right? And this one, this is the response. This is the disturbance, right? So in the case where the system is linear, my force is not very large, then this response I know will be proportional to the force, right? So this is a linear disturbance, linear response regime. And so what I have is this is my force I apply at certain time t prime, and this force could be continuously varying, time varying, and then from the start of time to the current time, because this R and the T of the atoms in the system could be a function of time is changing because I apply the external force, right? And this is just related to a response function here. And that's the function that I'm interested. So B, A, and this is T prime. This I'm looking at the T, time T, so T minus T prime. So this is the instant that is acted. And after some time, what's my system response? What's this response, this quantity is responding, right? It's just the only assumption I have here is a linear small disturbance, so that this response is proportional to the first power of my force. So here, this BA, say phi, is after effect function. It's a general describe what happens after apply a disturbance to the system, right? So it should be a real observable, say real quantity. And this is in fact is also sometimes you probably some of you heard the causality, right? F is the cause, and later on it has a response. So you should not; those results are general. You cannot violate, and those are the causality requirement. Okay, so what we have written is in real time. And of course, you can always express those properties in the frequency domain. You can do the Fourier transform of force. And if you do your Fourier transform, and we have here, I should do the ensemble average. I want to look at the Fourier transform. And then I can use the Fourier space response, and I'm not going to derive it, but this can be proven. And at BA, so this is the disturbance start with A, and disturbed quantity due to that force, and the response is a specific response. For example, like I said, viscosity. So here is a frequency, and the force is also Fourier transform and exponential I omega t and d omega. So you can say that this susceptibility that we usually call dynamic susceptibility of the system must be related to the after effect function here, right? In fact, this susceptibility, so here we have dynamic susceptibility of the system, XBA omega is actually the Fourier transform of, so it's 0 to infinite phi BA tau exponential mass I omega tau d tau. So if I know this, I know the after effect function, or if I know after effect function, I know the susceptibility. Okay. And in fact, there is a really interesting relation between this one could be real part and imaginary part. Because I'm here I have, in the Fourier transform, I have I there, right? So I have a real part. I have an imaginary part. I can write, okay, I have a real part plus I imaginary part. And both are frequency dependent. And you can say, because this is really just a cosine or sine part of the Fourier transform, if I do a cosine, so if I know real part of this frequency dependence, I can go inverse cosine transform and get this function here. From this function, I can do a sine transform. I can get the imaginary part, right? So which means the real and imaginary part are always related. And this relation is the Kramer-Kronecker relation. It's very general. If you do thermal radiation, you probably heard, for example, the dielectric constant or optical constant. You can calculate, if you measure real part, you can calculate imaginary part. If you measure imaginary part, you can calculate real part. That's an example of the Kramer-Kronecker relation. And so the real part, for example, can be calculated from an imaginary part, and minus infinite to plus infinite, imaginary part, omega prime, and omega prime minus omega d omega prime. So you can say the problem of this integration is that when omega prime equals to omega, because I'm integrating from minus infinite to plus infinite, this blow up. So this has to be, this is in the front, you put a Cauchy principal value. So actually, there's a negative sign for this part. And that's just to say when they going from left approaching to omega, or from right approaching to omega is separated due to the limit at this singularity point. And similarly, there is a relation. You switch, there's no more sign. It's a positive sign. You switch this with this, you get another relation. So either way, if you know the real and know imaginary part, but you need to say, if you look at this function here, you need to know the whole function as a function of frequency, right? If you just have, if you do optical measurement and you know only a section of that, you may not be accurate enough to do this inverse using the Kramer-Kronecker relation. And there's this is a causality. What sometimes people say this is a causality requirement, right? You can say that we don't have assumptions there. And what's also interesting, right? If you say this is a response on different phase space variable, but if B is the same as A, right? And A is related to the, because the A is here, is a disturbance to the Hamiltonian, right? The energy of the system. So in fact, when B equals to A, there's a useful relation that's B equals to A. And what we have is the energy dissipated in the system due to this external disturbance, right? And equals is related to the imaginary part of the dynamic susceptibility. So omega over 2 V x AA, so B equals to A now, the imaginary part, and omega F omega square. So this is just a result out of, again, the causality, and it's general. Okay, and here we're discussing the response function. And next, let's move on. So I have now the system has a small perturbation, H prime. And initially, it was at an equilibrium situation, right? We have F, say, the H0. And now after this perturbation, the distribution function will change, right? Because the Hamiltonian of the system change, and distribution function changes. So now you see the approach I mentioned before. One of those approaches is going to Boltzmann equation. The Fn, the n particle distribution function, is reduced to one particle distribution function, and that's the Boltzmann equation approach. And what we go in this approach is a linearize, is actually taking the n particle distribution function. So the linear response theory start from the Liouville equation, and but it's a linearized Liouville equation, but still keep the n particle distribution. So if we go back to the Liouville equation, and this is a Liouville equation written in operator form. So the Liouville equation is an equation for the n particle distribution function as a function of time. And we could write this in operator. So it's the H, the Hamiltonian of the system, and the Fn. This bracket is called the Poisson bracket. I'll explain what it means. And then see there's also another notation. And this is using I gamma operator and the Fn. Okay, here the point is I'm writing a Liouville equation with n. This is the original Liouville equation with the n particle distribution function. And notation-wise, what do we have on the right-hand side? First, that's the curly bracket. Is a Poisson bracket. And that's just a notation if you have A and B. And what it means is because I have I particles, so I equals 1 to, in fact, say these are the total number of degree freedom. If I have capital N particle, and each particle has a 3 degree, that's a 3n. If it's a 6 degree, it's a 6n, right? So this is a, and then I have dA and dRi, dB, dPi minus dA, dPi, dB, dRi. And with this notation, you put it back into the right-hand side, you get back to the original Liouville equation that we have written down before. Okay. And this one, gamma here, is an operator. So gamma is definition is an operator is minus I, and H, and whatever behind this function is put in here. This is the operator notation. Okay. And the use of this is the Liouville operator. The use of this Liouville operator is now with this written as this form, you can just think this is like an ordinary differential equation. Okay. And you have to go back into all this detailed math. But think this as an ordinary differential equation. You solve it as an exponential function. That's the use of this Liouville. And of course, the gamma, you keep it as an operator form. And now, so what do we have? The system Hamiltonian is H0 plus H prime. Right? I have a perturbation to the system energy. And then correspondingly, the n particle distribution function is F0n. That's corresponding to equilibrium. And then small perturbation F1, and that due to the perturbation H prime. And F0n is related to, because it's at equilibrium, so it's you can write it as HKBT. That's a Boltzmann distribution there, right? For system, so the way that I'm reading here, F0 here is a canonical distribution, canonical system, right? And so once I have those, I put in here into this equation. I use the operator, and I neglect the term I neglect is H prime times F1, because that's H prime is a lower order, small disturbance, F1 is small disturbance. So I drop that cross term, that's a higher order. And with that, I can solve for F1 in the operator notation. So I will have F1 n and T R P, right? That's the phase space variable, or is a V KBT. That comes, the V KBT comes from F0n, and minus infinite to T, and exponential minus I, T minus T prime, gamma, right? If you look at this exponential that come from, I treat that gamma just like a constant. I do integration. That's the operator math there. And gamma 0, this gamma 0 is corresponding to when H is H0. And then I have the time derivative of this, because H prime has A, so I have time derivative. In the A, I have R is a function of time, and P is a function of time. That's why I can do the time derivative. And I have F T prime, and this is a T, or T prime. And then I have F0 to N and D T prime. So this is the solution to the perturbed distribution function, n-particle distribution function. Remember, gamma is an operator. So it looks simple, but it's an operator. And for this operator, in fact, if you want to operate what's the function behind, you have to expand this back into using the Taylor expansion, so that you can't just put this stuff inside the exponent. Okay, so what's the use of this is, once I have this formal solution, I can go back to calculate the ensemble average, right? Because my ensemble average is any quantity in terms of the momentum and the location of the system times distribution function. Now, distribution function consists of for equilibrium part and the perturbation part, right? In most transport, if I deal with transport, I know that equilibrium part will drop out, and this is the deviation part that gives me the response, right? So I do this. I go to calculate, and for example, we were writing this before. The response will be, you can say this is once you do the substitute into the n-particle averaging expression, at the end what you get is dt prime ft prime. That's the and then here we have v kbt and integration of f0n, and then we have b r p t and exponential mass I t mass t prime gamma 0 a dot, and here I have r t prime p t prime and dr dp. Okay, and here the bracket. And the reason I'm writing into this form is because inside the bracket is my after effect function, right? This is the disturbance. This is the response I'm interested in, the quantity of response. And this one is my after effect function due to that disturbance that created the A, which is the phase function in the Hamiltonian. So this one is my after effect function BA T minus T prime as I defined before. Right here I have a T minus T prime. And if you use further the operator notation, this one, the operator properties, you can get the following. So here we're not going to write all the derivation. I know this is a pretty lot of writing. I want you to appreciate, right? Because I said before, you have Boltzmann approach, you have linear response theory approach. And linear response theory is really developed after the computational power, say, in combination with the computational techniques. So T minus T prime. Now, if you look at this, it could be V KBT. After you actually do this operation, use that, let's say, operator properties, and we can say here is F0n, and A dot, that's a time derivative, RT prime, P T prime. And look at the time origin is important. B here is RT minus T prime because of this operator, and P T minus T prime. So now this is the quantity in the time before dr dp, right? Here you can see this is this phase space average, because here is a distribution function, equilibrium distribution function. And this disturbance is out. It actually does not get into my A, does not get into my B. It's independent of that disturbance. This is when I do thermal conductivity viscosity is a physical property of the system, right? And this is a statistical, the ensemble average, because here that's what we define. And this is the quantity at two different times. So this is a cross correlation function. And with this, you can convert also back into the time, because we say it's an ergodic system, right? Here is the ensemble average. Now you can convert back into the time average. So we could write this KBT. That's the ensemble average of quantity T minus T prime, and the quantity at the T prime derivative. And this is this time origin is not important, so you can write T and A at this origin you choose, whatever time is 0. And this one, there are different ways to write it. You can write V KBT, and rather than the derivative of A, you can write in derivative of B and time T. And this all can be proven. I'm just giving you the expression. And what it means here is all time averaging, the ensemble averaging. But when I do molecular dynamics, I do the time averaging, because so what it means is I have this ensemble averaging is equal to time averaging. So T prime plus T and A T prime, right? So the bar in the up is the time averaging as we introduced. So now we have, so you can simulate an equilibrium system and get the properties with the response, because the force is taken out. Okay. And with this, of course, you know the after effect function. You can get the frequency component, right? As we have written down the susceptibility as a function of frequency. And in fact, if you write further, because the susceptibility now can be calculated as here, if I look at this one, the autocorrelation, when A goes to itself, that's an autocorrelation. When it goes to different quantity, it's a cross correlation, right? So now the imaginary part can be related to the autocorrelation function when B equals A. And what you have here, that from that expression, I can write the imaginary part of the susceptibility as a function of frequency is V omega and 2 kBt, and mass infinite to plus infinite exponential mass I omega t, and A at the t, A at 0 dt. So from the cross correlation, the autocorrelation, I can calculate imaginary part. And this is, I mentioned it many times, this is actually the fluctuation dissipation theorem. This is the fluctuation, autocorrelation. The imaginary part is the dissipation, because that imaginary part is related to the energy dissipated in the system, right? So this is the fluctuation dissipation theorem, general form. And when I do, for example, near-field radiation simulation, we use a lot of this fluctuation dissipation theorem. And what I do is the current fluctuation is related to imaginary part of the dielectric constant. That's one example of the fluctuation dissipation theorem. And if you do the quantum, you can generalize in the quantum limit. And what you have here, the imaginary part, you will have to write this as h bar and the cotangent. So this is a hyperbolic cotangent function, h bar omega 2 kBt, and mass infinite to plus infinite exponential minus I omega t, and A t A0. So that's the quantum form of modification to fluctuation dissipation theorem. Okay, so now this is the essence of the linear response. And what I need next is to give you a few examples. For example, how I can relate the electric conductivity and calculate it based on if I have ions in the system, right? So writing down the corresponding form. So if I have ions in the system, and I apply an electric field to the system, and so now each ions will be, so the field will give a force. Force will move the ion, and force times distance, it gives me the work, right? That's the additional energy that the system is subject to perturbation, right? So we have then look at the perturbation in Hamiltonian can be written as I equals 1 to n particles, and the displacement Ri, you can do Ri minus R0, but let's say then R0 is the original Hamiltonian, right? So it's Ri, and then the force is the charge. So I have the ith atom has, say, the ions Zi charge, and I have then E, which is a function of time, right? This is the perturbation. And from here, going back to the definition, I know my A, because I want to express A in terms of the phase variable, right? This should equal to, according to my definition, mass A V E, which is my disturbance. And so my A here then equals minus V sigma I equals 1 to N Zi E Ri. Okay. And I can look at, for example, current. What's my response? Right? Given an electric field, I want to look at what's the current in the system. So my current of the system is the charge times velocity, right? So the current in the system is charge times velocity. So Zie and Dri dt. I equals 1 to N, right? And so I do in terms of the per unit volume again. And you can see here, I was a little bit, I'm trying to reconcile my sign. I haven't been able to reconcile my sign. So I write this as the gradient because here is dr dt, here is dr dt. Right? Okay. So with that, I can then now look at it. This is essentially, this is the response I want to look at, and that's my B. Right? So I have A, I have B, and now I can use the expression we have, the after effect function, and in fact what we have here is, if I write into the frequency form, J omega equals the electric conductivity, which is usually tensile. Okay, thermal conductivity is tensile, electric conductivity is tensile, and 6 component, and is related to the tensile product to the electric field. Right? That's the response. And this is the after effect. That's the frequency component. Here is the real-time component, and that's a frequency expression. And I can use the real-time, real component. And so what I have here, then the electric conductivity So the electric conductivity, if you use what we have here, can be written, particularly if I do isotropic. I can write each direction, but now I do isotropic, so then I don't have all the tensor component only diagonal. And in that case, I can average, so it's 3 kBt. And 0 infinite J xt J0 Jx at 0 and plus Jy t Jy at time 0 Jzt Jz at time 0. Time 0 is the origin you choose, and then I have exponential mass I omega t dt. So this is my frequency component of the electric conductivity of this system I simulated. So in a real simulation, you solve F equals ma if you know the force interaction between these atoms. And once you have that, you write the time derivative. That's your current flux. And then you calculate those time autocorrelation function. And we'll say 1/3 because I say isotropic, so that I'm averaging over 3 directions. Right? So this is, in fact, what we have here is the Green-Cobo formulation. This is the Green-Cobo formula. Green-Cobo formula. Right? We can write from the, say, we can calculate the time response, and from there we can calculate also the frequency. It's a simple frequency, the Fourier transform. Okay. And Green-Cobo is, they didn't write one paper, they developed this as independent of each other. So this is the case for the electrical, the expression, final expression for the electric conductivity. And in fact, say, to derive a Green-Cobo formula for thermal conductivity was not easy. And the reason for that is, in this case, the derivation process, we were using the system have an external disturbance, F, right? And the thermal is an internal disturbance, the thermal fluctuation of the system. And there are many derivations. The cleanest derivation, which doesn't have any simple, any physical, meaning, was actually using gravitational field to drive the molecule as a disturbance and derive the heat flux correlation. But say what we need is the book when I present this, in fact, I'm still not very comfortable about that section. So what we have for thermal disturbance, and the distribution function is exponential. We can write exponential the Hamiltonian H, the energy, a small volume, and KB T plus delta T. Let's suppose, so what I'm looking at is the temperature fluctuation inside the system. Because of the temperature fluctuation, the local energy has a fluctuation. And I want to write what's H prime. The case I want to write what's H prime, right? And with this distribution, and I can write from here, I can write H prime equals, if I linearize it, is H itself, which is the energy Hamiltonian, which is a function of position and velocity, for example, is T, delta T, which could be a function of R, and T, and D integration over the volume. So this is my H prime, right? And then you have to plug in this H prime and go back to the derivation and find that what's the F1, okay? And in the process, I have to use energy conservation, and then I was say, then you have to integrate over the volume you're considering and what's the boundary condition. You check, and I looked into many books. I was never satisfied, and I put what I finally say, I have to complete this. So you can check my book. And so if you do this, what you have is you will derive a thermal conductivity tensor. And this is because I have now a delta T in the system, right? Temperature fluctuation. And from temperature, this delta T, I can eventually derive a thermal conductivity tensor that is V KB T squared 0 to infinite, and the heat flux expression at tau, and the autocorrelation of heat flux between 0 and tau exponential mass I omega tau b tau. So this is the Green-Cobo expression for thermal conductivity. And thermal conductivity itself, again, could be a function of frequency. Because normally when we do heat, we don't do very high temperature, high frequency. So this is, in fact, this is related to the Cantonian equation. But Cantonian equation is never correct. I made the comment before. Well, it's very hard to be correct because when you have a very fast temperature disturbance, you typically have a spatial temperature gradient. And if that gradient is longer, shorter than mean free path, you can't just use Cantonian equation. So what you should do is actually write both frequency and space dependent. So time and space dependent thermal conductivity. And that gives you long no-core thermal conductivity, which will be not only a function of frequency, but also be a function of wave vector. Nobody has done that, okay? I'm just telling, I think that should be the case. And in fact, you see the derivation I had before, the F, I said the system is a uniform force. Here, that disturbance temperature could be spatially dependent. If that's spatial dependence, you can write actually corresponding space dependent wave vector and frequency dependent expression, thermal conductivity. Okay, so now you have Green-Cobo, and the beauty, you should say here the beauty is it's an equilibrium simulation. You simulate a system box up there. Even though we say the derivation process I have external force, but at the end all those transport property is I don't have disturbance anymore, or say external force anymore. I just can simulate the equilibrium system and do my autocorrelation function and calculate transport properties, viscosity, all those. But you have to have the expression for what's the microscopic JQ. In the case of current, I have expression here, right? So deriving those microscopic expression for the quantity of your interest is the next step. So what are those microscopic quantities? Right? So for example, kinetic energy, I want to calculate, that's very easy. Say I equals 1 to n, and pi squared to m. Right? And you can write the kinetic potential, Hamiltonian, add up kinetic and potential. So simple ones are easy. And for heat flux, and they're also heat and mass flux, in fact, is very easy, right? The mass flux is just the quantity is mvi of say mivi, and I equals 1 to n. And now if you do your heat flux, and the heat flux is I equals 1 to n, and vi, hi is the enthalpy of per molecule or atom you're dealing with, and plus 1/2 of the interaction I equals j equals 1, j does not equal to I, and rij, that's the distance between the two atoms, and fij dot vi. So this one is this expression is actually derived from really you write the energy conservation for each atom, and in the process you can derive the expression, microscopic expression for the thermal, the heat flux. Okay, and there are many different microscopic expressions for different quantities. The final comment I want to make is when you simulate, so here in the derivation, linear response theory, I am doing actually a canonical system, right? Constant temperature. Now, when you do a molecular dynamics simulation, you typically fix the number of atoms. You try and maintain the energies constant, right? And then when you have a constant energy, constant volume, constant number of molecules, what do you have? You have a microcanonical ensemble, right? So how you can do a microcanonical simulation and yet to represent that I'm simulating a system as constant temperature or I'm simulating a system of constant pressure. And this is people have spent a lot of time trying to deal with that question. And here is the so how you thermostat the ensemble. Thermostat ensembles. Okay. So to do this, you actually also have to get used to the fact that normally you do F equals ma, right? That's the equation of motion. But there are many different ways to write the F equals ma. And there are Langevin equation of motion, Hamiltonian equation of motion. They are all equivalent. Not Langevin, Lagrangian equation of motion and Hamiltonian. So, for example, when you do Lagrangian, equation of motion, right? And what you use is r dot. Okay, that's you use this the velocity and space as your as your variable, and you construct the Lagrangian of the system, which is a function of time, function of r, function of velocity, and Lagrangian of the system is r dot minus the potential energy. So it's kinetic energy minus potential energy. Maybe you learned this in dynamics. And so the Hamiltonian principle, so what's the Lagrangian equation of motion? There's this Hamiltonian principle, say when your system go from point 1 to point 2, the Lagrangian, so the integral here, integral, this is the action integral from 1 to 2 of the Lagrangian T r dot, and you integrate over time. And this should be extreme. It's maximum or minimum. And in fact, I don't know whether it should be maximum or minimum. But say its derivative is 0. Okay? Derivative is 0. From there, you do variation. You actually get the equation of motion for the Lagrangian. So you do your here, you do the equation of motion, then you will get, this is the extrema, you get dl dr. Here I'm writing in each component the velocity, and dl dr itself equals 0. So this is actually F equals ma under the Lagrangian. Okay. The Lagrangian is useful, but it has one defect. It's not symmetric. Okay, it lacks symmetry. And so if you rather than use r and r dot, if you use r and p, this will come back to the phase space, right? If you use the position and momentum, and you actually can do a transformation into the Hamiltonian equation of motion. So you can write, rather than using r, if you do your new variable p momentum, if you define equals the Lagrangian derivative, that's your momentum, and you can go write the Cartesian coordinate, you'll find this all come back to F equal ma. Everything makes sense. And then you can construct your Hamiltonian TRP. So now my variable in Lagrangian is r and r dot. In Hamiltonian is r and p, right? So in the so this is sigma dl d ri mass L, and you can say in the simple say case of kinetic plus potential is essentially if in Cartesian coordinate you really say kinetic energy plus potential energy. This is what we typically think about the Hamiltonian. Okay, and once you have the Hamiltonian, you write the equation of motion for Hamiltonian is Ri, and so the momentum derivative and space derivative is dH dPi. So this one you can say compared to Lagrangian equation of motion, this is a Hamiltonian equation of motion. The momentum and space derivative, and they are symmetric. So that's the Hamiltonian is often used. Why I'm saying this? Why I don't say I'm going into rather than F equal ma Lagrangian and Hamiltonian? That's because, well, sometimes, for example, if you if you do a simulation of molecules, right? The molecule, of a diatomic molecule has, of course, each molecule has 2 atoms. If you say I'm going to simulate just r position and velocity, I have to split this molecule into 2 atoms, right? But say I can use theta, say the angle, rotation, and the relative vibration. So in that case, I have different variable, different momentum, different coordinate. So the beauty of the Hamiltonian is you can write that much easier. Now, what's the relation to this? My original question. I do a simulation. That's a microcanonical ensemble, right? And how I can simulate a canonical using a canonical, say to actually do a canonical system with constant temperature. And the trick here is this was a creating artificial Hamiltonian. Okay, so for example, Nose introduced a Hamiltonian, and the Hamiltonian he wrote. This is he wrote r, not only r but also additional variable, and the p prime, momentum, and the ps. Okay, and in his Hamiltonian, the time is t prime, and then they say it's not even the real time. The time is say related to, so it's dt equals s dt. So you have this additional s is your equivalent of 1 of the r, and then you have a p, additional momentum that was introduced, and he said this one equals sigma I to n p I prime, and 2m s squared plus potential energy is still the real space, but he has additional add another term, this momentum. So is this 2mn? So and plus here is nf plus 1, and kBt log S. He cooked this up. Okay? And the reason he cooked this up is you write the Hamiltonian, you can write the equation of motion. Okay? And he said if I simulate this system, even though I simulated it's a microcanonical ensemble, at the end I get a canonical ensemble result for the original system. So he actually proved it. So the way you prove it in a microcanonical ensemble, you remember the entropy is k log omega, right? Omega is the number of states, right? So number of states is really just dr dp prime, and now I have extra ds dps, right? And then this is a counting number of states, so is when the energy of the system is equal to the Hamiltonian, that delta, I have one state, right? So this integration is just a summation, what it says. So starting from here, using this Hamiltonian, integrate the S and the P prime, PS, right? These are the two extra he introduced. He actually showed that after your integration, what you have here is say NF plus 1. This is the last equation I'm going to write. 2 pi mn kBt 1/2 exponential e kBt. I thought this was beautiful. The people actually conjoined those ways of doing things. That's why I want to write to you. And this is H, R, P, and kBt. So you see the trick is he actually going from this delta, he was able to integrate the ds dp. And because he add this log here, right, in the equation of motion, he add this log, he got the exponent, and the convert back into here is your Boltzmann statistics, right? And you can also prove if you do a quantity of A and the R, say that's the time average is the same as the ensemble average, except the nose had one problem. Because so it was later Hoover said this was not necessary, and going back to actually go to real space, and that actually solve his problem. So this is called the Liouville-Van Hope thermostat, right? And there are people develop, say for example Anderson, he developed a thermostat where you can create a constant pressure system. So you have different so with that you can write different equation of motion. So you add essentially one equation into a system of n particles. You can solve the using that you can deal with constant temperature, constant pressure, different constructions and ensembles. Okay, 12:30. I thought I was going to show some slides, but remember, if you haven't done your evaluation, let's see, at least I use time up. Thank you.